Look up at the sky. It's a vast, beautiful canvas that stretches above us every single day, a silent companion to our lives. On a clear afternoon, it's a brilliant, seemingly endless expanse of blue. But have you ever stopped to truly wonder why? It's one of those fundamental questions we might learn as children, but the full science behind it is far more fascinating and elegant than you might remember. The question seems simple, but the implications are profound. If the sunlight that travels millions of miles through the black vacuum of space to reach us is essentially white light, a perfect mixture of all the colors of the rainbow, why isn't our sky a brilliant, glaring white? Why this specific calming shade of blue that has inspired artists and poets for centuries? And just as puzzling, why does this reliable blue canopy dramatically transform at the beginning and end of each day? Why does the sky blush with fiery reds, vibrant oranges and soft pinks during a sunrise or sunset, painting a masterpiece that is never the same twice? These daily transformations are not random, they are governed by the same principles that color our midday sky. The answer isn't just a simple fact, it's a beautiful story of physics. A delicate dance between light and matter, happening miles above our heads in the very air we breathe. It involves the fundamental nature of sunlight itself, the specific composition of our planet's atmosphere, and even the unique biology of how our own eyes perceive the world. Over the next few minutes, we're going to unravel this everyday mystery. We'll journey from the sun, tracing the path of a single photon as it travels through our planet's atmosphere, and finally, to the science of perception itself. By the end, you'll not only know why the sky is blue, but you'll also look at every sunrise and sunset with a newfound sense of wonder and a deeper appreciation for the incredible physics at play. So, let's begin our exploration into one of nature's most spectacular and constant displays of science. For thousands of years, humanity has looked up in collective wonder. We've gazed at the vast blue canopy above us, a constant presence that frames our lives and serves as a backdrop to all of human history. It has inspired art, mythology, and the very first stirrings of scientific thought. Philosophers, poets, and curious minds of every generation have all asked the same simple yet profound question: why is the sky blue? Early thinkers proposed explanations rooted in what they could observe. The ancient Greeks, for instance, believed the sky was a manifestation of a divine, fiery substance called ether. For centuries, a very popular and intuitive idea was that the sky was simply reflecting the deep blue of the world's great oceans. Others, like Leonardo da Vinci, correctly deduced that the air itself had something to do with it, theorizing that sunlight was altered by tiny particles suspended in the atmosphere. These were noble attempts to decipher a grand, cosmic puzzle, representing the dawn of our quest to understand the natural world. But the true answer isn't found in mythology or simple reflection. It's a beautiful story of cosmic collaboration, a precise, physical process that occurs every single second of every day. The real reason for our blue sky is a delicate dance between three key players: the pure, white light traveling 93 million miles from our sun, the unique composition of Earth's protective atmosphere, and the fundamental principles of physics that govern how they interact. To truly appreciate the answer, we must first understand each of these players individually. In this journey, we'll unravel this mystery piece by piece. Sunlight looks white, but it's actually made of many colors. Each color has a different wavelength. Earth's atmosphere is filled with tiny particles. When sunlight enters, it doesn't travel straight, it scatters. Shorter wavelengths like blue scatter much more than red. This is called Rayleigh scattering. Even though violet scatters more, our eyes are more sensitive to blue, and the sun emits more blue light. At sunset, sunlight travels a longer path. Blue light scatters away, leaving red and orange. Now that we've unraveled the beautiful physics behind our blue sky, it's time to tackle some of the most common and persistent myths surrounding this daily spectacle. Science is a process of questioning and refining our understanding, and that includes correcting ideas that, while perhaps intuitive, don't quite hold up to scrutiny. These popular explanations often feel right, but the reality is usually far more interesting. Let's bust a few myths. The first and perhaps most widespread misconception is that the sky is blue because it reflects the color of our planet's vast oceans. It's an easy connection to make. We have a big blue thing above us and a big blue thing below us, so it seems logical that one is simply a mirror of the other. After all, over 70% of our planet is covered in water. The sheer scale of the oceans makes it feel plausible that they could paint the entire atmosphere. However, this idea is fundamentally backward. The sky's blue color is entirely independent of the water on Earth's surface. Think about it, the sky is just as brilliantly blue over vast landlocked deserts like the Sahara, the sprawling prairies of North America, and high-altitude mountain ranges hundreds or even thousands of miles from the nearest ocean. If the ocean were the source, the sky's color would fade the further inland you went, becoming paler over continents, which simply isn't the case. The truth is actually the reverse. While water does have a very slight intrinsic blue tint due to how its molecules absorb reddish light, a large part of why the ocean appears so deeply blue is because its surface is reflecting the blue light from the sky above it. The sky gives the ocean much of its color, not the other way around. The ocean's final color is a complex mix of this reflected skylight, its own subtle blue, and colors from sediment or algae. But the sky is the dominant contributor to that classic azure hue. This leads us to our second point of confusion: the nature of space itself. If our atmosphere is what makes the sky blue, what happens when you leave it? The answer is profound in its simplicity. Space is black. On the moon, which has virtually no atmosphere, the sky is always a deep, star-studded black, even when the sun is shining brightly. This is the ultimate proof of Rayleigh scattering. Without a dense blanket of gas molecules to intercept and scatter sunlight, the light travels in an uninterrupted straight line from the sun to your eye. There is no medium to scatter the blue light in all directions, so there is no ambient color. You only see light when you look directly at a light source, like the sun, the earth, or distant stars. The vast emptiness between them contains nothing to illuminate, and therefore, it appears as a perfect inky black. Astronauts aboard the International Space Station witness this daily. The razor-thin electric blue curve of our atmosphere is a stark boundary between the colorful world below and the absolute blackness of the cosmos. The beautiful blue glow we cherish is a phenomenon confined to that thin, precious shell of air surrounding our world. Finally, let's look up at the clouds. If the sky is blue due to scattering, why are clouds a brilliant white, or sometimes a menacing gray? This is another fantastic question that reveals a different kind of physics at play. The myth here is that clouds are white for the same reason the sky is blue. They aren't. The key difference is the size of the particles doing the scattering. Rayleigh scattering, which gives us our blue sky, happens when light interacts with particles that are much, much smaller than the wavelength of the light itself, in this case, individual nitrogen and oxygen molecules, which are only fractions of a nanometer in size. Clouds, however, are made of water droplets or ice crystals. These droplets are vastly larger than air molecules. They are, in fact, larger than the wavelengths of visible light, typically measuring several micrometers across. This thousand-fold difference in size changes everything. When sunlight hits these large droplets, a different process called scattering occurs. Unlike Rayleigh scattering, which is highly dependent on wavelength, scattering is not. These large droplets act like tiny, imperfect disco balls, scattering all the colors of the visible spectrum: red, orange, yellow, green, blue, and violet, more or less equally in all directions, but especially in the forward direction. When all the colors of the spectrum are scattered and mixed back together, our eyes perceive the result as white light. So, clouds look white because they are excellent non-selective scatterers of the entire visible spectrum. And why do they sometimes turn gray? It's a matter of thickness and light absorption. As a cloud becomes thicker and denser with water, less sunlight can penetrate all the way through it. The top of the cloud continues to scatter all light and appears bright white, but the base of the cloud receives very little light, as it has been scattered away or absorbed by the layers of droplets above. From our vantage point on the ground, we are looking at the poorly lit bottom of the cloud, which appears dark and gray, often signaling impending rain. Here's a myth you can test yourself: the idea that polarized sunglasses just make everything darker. While they do reduce overall brightness, their main function is to cut glare by filtering out light that is vibrating in a specific orientation. Light from the sun is unpolarized, meaning its waves vibrate in all directions. But when this light scatters off air molecules to create the blue sky, it becomes partially polarized. The effect is strongest when you look 90 degrees away from the sun. Polarized sunglasses have a filter that blocks light polarized in a certain direction, usually horizontal. Because much of the scattered blue skylight is polarized, your sunglasses can block a significant portion of it. If you tilt your head while wearing them, you'll notice the sky's brightness and color change, proving that the blue light above is not just colored, but also has a hidden property of polarization. Our final myth relates to altitude. One might think that getting closer to space would make the sky a lighter, paler blue. The opposite is true. The sky at high altitudes, like on a tall mountain or in an airplane, is a noticeably darker, deeper shade of blue. Why? It comes back to the density of the atmosphere. At sea level, you are looking up through the entire dense column of air. There are countless molecules above you to scatter blue light towards your eyes from all directions, creating a bright, rich blue. As you ascend, there is less atmosphere remaining above you. With fewer air molecules to perform Rayleigh scattering, less blue light is scattered into your line of sight. The sky becomes less bright and more of the blackness of space begins to show through, resulting in that stunning, deep indigo. So, from the ocean's reflection to the whiteness of clouds and the darkness of space, understanding these common myths only deepens our appreciation for the specific elegant physics that paints our sky blue. Sunlight is a mix of colors, and in air, tiny molecules scatter the shorter wavelengths most. This is Rayleigh scattering. The sky looks blue because blue light is scattered in all directions more than other colors, and our eyes are especially sensitive to it. At sunset, the longer path through the air scatters blue away, leaving reds and oranges. Subscribe and keep exploring the answers to more science questions.